Dear all, a grand welcome to Woutons Edis Online. In this session, we are going to discuss some important questions from control system stability analysis. Consider the first question. We have a closed loop system. We want to take the stability of the system in terms of K. That means we want to take asymptotic stability of the system in terms of the feedback gain K. Options are given in terms of K. Here, the feed-forward transfer function g of s is equal to s minus 4 divided by s plus 5 and a feedback gain of k. We can obtain the transfer function t of s that is equal to g of s divided by 1 plus g of s h of s. That is equal to s minus 4 divided by 1 plus k multiplied by s plus 5 minus 4k, from which we can obtain the characteristic equation. Now we obtain the characteristic equation as 1 plus k multiplied by s plus a constant term 5 minus 4k. We formed Routh array. The condition for stability is the coefficient of s in characteristic equation must be positive. That means the elements in the first column of Routh array should be positive. That means 1 plus k greater than 0. That implies k greater than minus 1. And the constant term 5 minus 4k greater than 0. That implies minus 4k greater than minus 5, or k should be less than 5 by 4. So actual range of k is minus 1 less than k less than 5 by 4. But in the question it is given k is greater than or equal to 0. So the range of k is 0 less than or equal to k less than 5 by 4. So option A is the right answer. Now consider the second question. We have a unity feedback closed loop system. We want to find the stability of system in terms of gain k. Options are given in terms of k. Here the feed forward transfer function g of s is equal to k multiplied by s plus 4 divided by s plus 1 into s plus 2, and feedback gain h of s is equal to 1. We can obtain the closed loop transfer function as t of s is equal to g of s by 1 plus g of s h of s, as shown in the equation. Now the characteristic equation is s square plus 3 plus k multiplied by s plus a constant term 2 plus 4k is equal to 0. So we can form Routh array. So the system to be stable, all the elements in first column of Routh array is greater than 0. That implies 3 plus k greater than 0, or k greater than minus 3, and 4k greater than minus 2, or k greater than minus 1 by 2. And in question it is given that k is positive. That means k greater than 0. So we can obtain the range of k as 0 less than k less than infinity. So k greater than 0. So option C is the right answer. Look at the third question. We have a unity feedback closed loop system. We want to obtain the frequency of sustained oscillation. The sustained oscillation is due to the presence of a single pair of poles on the imaginary axis. So the system is marginally stable. We want to find the frequency of sustained oscillations. Options are given. Here the feed forward transfer function g of s is equal to k divided by s into s plus 2 into s plus 4, and it is a unity feedback system, so h of s is equal to 1, and the closed loop transfer function is equal to k divided by s cube plus 6x square plus 8s plus k, from which we can obtain the characteristic equation. From the characteristic equation, we formed Routh array. For the system to be marginally stable, one element in the first column of Routh array should be 0. That happens when 48 minus k divided by 6 is equal to 0. From that condition, we can obtain the value of k for which the coefficient of s raised to 1 is equal to 0. That implies 48 minus k by 6 is equal to 0, or 48 minus k is equal to 0. That implies k is equal to 48. Then we can obtain the frequency of oscillation by forming the auxiliary equation from Routh array. From the Routh array, we can obtain the auxiliary equation as 6s square plus k is equal to 0, from which we get s square is equal to minus 8, or s is equal to j root 8. And we know that s is equal to j omega. So the frequency of sustained oscillation omega is equal to root 8. That is equal to 2 root 2 radian per second. Okay, thank you. Bye.